Okay, we are rolling through acids and bases. So last time we got into talking about how to do several different types of calculations. Obviously, we talked about the pH scale, which is the scale, again, that you really do want to kind of follow to help you determine if it's acidic, basic, or neutral. Again, below 7 is acidic. Above 7 is basic, and as we talked about, technically speaking, dead on 7 there is neutral. To calculate the pH, we use the formula. The pH is equal to minus the log of the H plus concentration. Remember, we talked about sort of how to put this into your calculator correctly. So if you have a display calculator, as we talked about this one and all the other ones, you pretty much punch it in exactly the way the formula is written. So you go negative log button, and then obviously your concentration using your exponent button when you do it. If you have that non-display calculator, like we talked about, again, this one and pretty much all the rest of them, you kind of need to work backwards. So you would need to put the number in first, then hit log, and then obviously the negative button. There's also a similar scale that doesn't measure pH, but measures the OH minus concentration. That was known as the POH, and that is minus the log of the OH minus. Again, it's really calculated the same way. A reminder, as we talked about, when you're trying to determine if it's acidic, basic, or neutral, go with the pH number. It can only be one of those sort of answers, as we talked about. And again, very common. People calculate both of those and give basically two answers. You know, it's acidic and basic at the same time, but always go with the pH. The nice relationship between those two is pretty much the pH plus the POH is equal to 14, which means it can sort of help you get around and sort of calculate things a little bit quicker. If you're just given the OH minus concentration, you get the POH, so basically subtract 14, you have the pH very quickly by just doing that, and obviously vice versa. We also talked about the idea that if you do have the pH, you could get the H plus concentration directly from that value, and that is the inverse log of the minus pH. And again, on most people's calculators, that is like the top left button there to shift, the second button, and the LOG button that usually has like a 10 and an X on top of it. And usually when you do hit that correctly, on most people's calculators, it will kind of display like a 10 and a caret on most calculators. And again, you want to make sure you do negative and make sure you hit that pH as well in that particular case. POH, you could get the OH minus concentration from it, and it is essentially the exact same calculation. It is the inverse log of the minus POH. And again, when you hit that calculator, that will get you 10 and a caret to the minus POH. That in combination there with our KW, which is our H plus, and our OH minus is equal to 1 times 10 to the minus 14. It gives you a variety of ways that you could sort of calculate these things. Any questions on any of that stuff we talked about last time? Okay, so I think we left off maybe with doing some examples. So why don't you take a few minutes here and do this example. We'll start with the first one. We have a solution that's the H plus concentration of 3.6 times 10 to the minus 9. So we do have the H plus concentration, and really from that we could directly calculate two things. We could calculate the OH minus concentration using KW, but in this case we're looking for the pH, so we definitely could directly calculate the pH from that. So the pH again would be minus the log of the H plus concentration, or again H3O plus, same thing, minus the log of 3.6 times 10 to the minus 9. So again, if you have a display calculator, you should hit the negative, the log button. You should hit 3.6, your exponent button, and the negative button, and 9. If you have a non-display calculator, you should go 3.6, exponent button, negative button, 9, and then hit log, and then hit the negative button. And either way there, you should end up with an 8.44 in terms of the pH here. First off, any questions on that calculation? Now, once we have the pH, we really can use the pH plus the POH is equal to 14. And that's really an easy way to get to the pOH, which would be 14 minus the pH, which would be 14, in this case, minus 8.44. And looks like a 556 here for the 556 for the pOH in this particular case. The other thing we also talked about was sig figs. So again, 2 significant figures here. Again, doesn't give me sig figs on the pH, but gives me decimal places. So 2 decimal places going that way. Acidic, basic, or neutral, this one? It is basic. We would want to look at the pH there, which is obviously above 7. So this would be a basic solution. Any questions on any of that calculation there on that one? All right, looking at the second one there, just do that. In this case, we're given the OH minus concentration. And again, just in general, the 2 things you can get directly from that would be, again, the H plus using KW, or we could directly calculate the pOH here because we do have the OH minus. So that would be a good place to start for this problem. The pOH, pretty much the exact same calculation, except that you're obviously using the OH minus concentration. Hence, the name tells you what you need. pOH, you should be using the OH minus concentration, minus the log, in this case, of 9.2 times 10 to the minus 2. And again, depending on which calculator you got going, this is how you should punch it in. Negative log 9.2 exponent button, negative button, and 2, and hit equals. If you got a non-display, you should start with 9.2 exponent button, negative button, 2, then you should hit the log button, and then you should hit your negative button. So again, those are the 2 ways that you would punch it in. And if you do one of those 2 ways, hopefully you should end up with, looks like a 1.04 for our pOH. Just like above, the easiest way to now get to the pH is basically just subtract 14. So our pH in this case would be 14 minus our pOH, which would give us 14 minus 1.04. Looks like a 1296 here on the pH. Any question on those 2 calculations there? Acidic, basic, or neutral on this one? Also basic, looking at the pH value, which obviously is above 7 in this case. Any questions on any of those there? Yeah. Yeah. So there's a relationship between pH and pOH that if you add them together, they equal 14. So it's a really good way that, you know, if you're, for example, in the second one here, you're really interested in the pH, but you're only given the OH minus, you could calculate the pOH like we did. And then all you simply have to do is basically take 14 minus it, and that will get you to the pH pretty quickly without having to separately go calculate kind of the pH using the pH equation. And vice versa, if you have the pH but want the pOH, you could calculate the pH obviously, and then again take 14 minus it, and I'll get you to the pOH without having to separately sort of calculate it by itself using the formula. Other questions? Yeah. The relationship is basically the pH scale, right? It goes from 0 to 14. So 14 is your max. Yeah. So basically, when you take it, if you remember, we talked about. Can I flip it? It's okay. Yes, for a sec. Yeah. 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 Okay. So actually, I'll do it right here. So if you remember, we talked about the pH scale that it obviously goes from 0 to 7 to 14, right? The pOH scale also goes from 0 to 7 to 14, but they do run opposites. So this is acidic on the pH scale. This is basic on the pH scale. This is actually basic on the pOH scale, and this is acidic on the pOH scale, which is why you should always look at the pH. But to answer your question, they basically are opposites of each other. So if you had, like we do here, like a 1.04 on the pOH scale, you'll have like a 12.96 over there on the on the pH scale, when you add them together, it equals 14. And that's why basically that's where the 14 actually comes from, is the relationship between those two scales. Basically, they're kind of both parts of the solution, if you will, right? And together you get everybody to 14. So that's where the 14 comes from. But again, as a reminder, don't even think about the scale. Yes, think about the pH scale. But that's really where the 14 sort of comes from. It's sort of both parts of it together get you to the 14. Other questions? Yeah. What's that? The pH in the second problem here ended up being 12.96, which is above 7, so it would be basic. So when you're trying to determine acidic, basic, or neutral, 100% of the time look at the pH, because pretty much everybody has this scale in their head, and that's what you should think about. Above 7 is basic, below 7 is acidic, 7 is neutral. And again, only one answer for those things, not both answers. So again, always look at the pH and I'll give you the correct answer. Other questions on that? Okay, so there's those guys. Scroll that across in case you want to see it worked out without scribbling. All right. Okay, let's try another example here. The pH is 5.67. Why don't we do a bunch of stuff on this one? Let's calculate the pOH. Let's also calculate the H plus concentration. Let's calculate the OH minus concentration, and let's determine, is it acidic, basic, or neutral? So starting with a pH of 5.67, calculate the pOH, the H plus, the OH minus, and again, acidic, basic, or neutral. A couple of things you get straight from it. You could obviously calculate the pOH directly from it, and you also could get the H plus concentration really directly from it, both of which we're looking for in this problem. We'll start with the pOH, and again, we could just simply use that relationship that we saw. pH plus the pOH gives us 14. That means that our pOH here would be 14 minus the pH, which is 5.67 in this case. And that would get us a lot of zeros on my calculator. 5.67. 833 looks like our pOH here. Any questions on that part there? While we're at it, we can again directly from the pH get the H plus concentration, and that would be the inverse log of the minus pH. So again, when you do that on your calculator, you're going to again hit basically top left corner on most calculators, the second or shift button, and then the log button, which on most calculators have like a 10 and an X above it. So that's what you're looking for. So we're going to do that. Usually we'll pop up a 10 and a caret. You want to make sure you make it negative, and we will go with 5.67 in this case. And again, if you have a non-display calculator, you do need to start with the number. So you would need to start with 5.67 and make it negative, and then hit shift log if you have a non-display calculator. If display calculator, you can punch it in exactly like it's written. And if you do that, again, no matter which calculator you're working with, negative 5.67, you will end up with here a 2.1 times 10 to the minus 6, and this would need molarity as it is a concentration here. Now, we could also, because we've calculated the pOH, pretty much do the exact same calculation to get to the OH minus concentration. The OH minus concentration would be the inverse log of the minus pOH. Again, when you hit this second and log button, you got your 10 and a caret. Make sure it is negative 8.33. And if you do that here, you end up with 4.7 times 10 to the minus 9 molar. Now, if your calculator is not in scientific notation, you might just have a bunch of zeros and like a 4 at the end, which is basically the same thing in terms of that. Question on those calculations there. So Is this acidic, basic, or neutral, this particular one? This one is right off the original number there, which is what we should look at, which is the pH. That is less than 7, so this should be acidic. Any questions on any of those things? Yeah. Is it for the two bottom ones you're talking about? Yeah, they're both negative. So yeah, you want to make sure you use your negative button, not your subtract button. Otherwise, you might get an error or the wrong answer. Yeah. Okay. Yeah. This one? Yeah. Are you asking how I got the formula or how I got that answer? So that is the no. So to calculate the H plus from the pH, that is the formula that I just boxed. That is the formula that you have to use to calculate the H plus if you have the pH value given to you, like we did in this problem. We had the pH value given to us. When you actually type into your calculator the inverse log by hitting the second button and the log button, on most calculators, it usually will pop up a 10 and a caret on the like display when you look at it. And then you want to hit the negative button and then the 5.67, which is the pH. And that number that you get when you do that will be the H plus concentration. Okay. Yeah, so where I write the 10 and the caret is guess what on most people's calculators sort of pops up when you hit the second and the log. Not everybody's, but most people, at least a 10 and a caret or a 10 and like the cursor bouncing up there on top or something like that is typically what you will see on most people's calculator. It's oftentimes what a lot of people have used for a lot of times for scientific notation incorrectly is kind of like that way of doing it. So yeah. Yeah. And so that's why, and then POH, yeah, so that's why we use it for that one. And that's how we would get our OH minus concentration for the same way. Yep. Okay. Okay. Yes. Either one. Whoever wants to go first. What's that? For the concentration? Let's see here. Let me try it one more time here. So negative 8.33, right? So on my calculator, I get it two ways. So on my calculator, I got a bunch of zeros and a 4 because I ran out of room. When I put it into scientific notation, I get 4.67 times 10 to the minus 9. So what did your calculator show at the end? Is this all zeros and a 5 or I don't know. It might just be the way they maybe rounded it to one significant figure because it's 4.6. So they might have flipped it up to a 5, maybe just on your calculator. Let me try it on this calculator, see what this one gives. Yeah, see on this calculator, it does give you a bunch of zeros and a 5. My calculator gives zeros and a 4 are the scientific notation. If we turn this into scientific notation on this one here, the actual number is 4.67. If you turn in scientific notation, I think it just rounded it because it had one significant figure, so it popped it up to a 5. So you would be, if your question is, would you be okay on that? You'd be okay. Yeah. If you are. Now, a couple of things in terms of, I'll be right with your question. A couple of things in terms of that question is you would be okay in the sense of that would be the right answer. It would be okay. But we do want to remember what we talked about last time, which is when we are going backwards, right? There are 2 decimal places, which means your concentration should end up at 2 significant figures. So if your calculator did give you that, you technically should write the 5.0 times 10 to whatever it is, the minus 9, to get the right sig figs. But if it's just an issue like that, you probably would be okay. I have 3 calculators. One did one way, one did the other. So, did you have a question or yeah? Say it one more time. No, they're not the same numbers in this case. On the top. No, what I was saying when I was talking was what you could calculate from that number is you could directly calculate the POH and you could directly calculate the H plus. So what I was saying at the beginning there was if you're given the pH, the two things that you could directly get from it is the POH like we did here and also the H plus concentration. Yeah, they're not equal to that. It's just those are the two things you could directly sort of calculate from it. Yeah. Are the exponents going to always be for? They typically are because they're basically based off of, if you had a pH of 14, it'd be 1 times 10 to minus 14. And the middle will be 1 times 10 to minus 7. So typically speaking, most cases you will have negative exponents if you're asking about, you know, kind of what these guys end up with. They typically will be negative. You do need it. So if you're asking, you do need to convert it to a negative number when you use this formula. Okay. Yeah. So when you use these formulas, you do have to make it into a negative. Otherwise, you won't get the right answer. And the answer, maybe the other question that wasn't asked is typically speaking, your concentrations, you will always end up kind of like a negative exponent. And for the most part, your concentrations, if you add up these two numbers, will usually equal about 15 when they, you know, they get like a 15 and when they add those two numbers together. Oddly, it's 14, but it rounds up to 15 in most cases when you do the scientific notation. Yeah. Yes. Yes. Well, we want everything. I think that's sort of box because we were looking for everything. I think. Let's just super zoom in there. No. So we want to know if it was acidic. This would be the H plus concentration. That would be the OH minus concentration. That would be the POH. So those are the 4 things that we were looking for. Yeah. Other questions? Yes. The KW. So if your question is, I'm going to say yes, and I don't mean to cut you off, but I think your question is, if after you get the H plus here, can you use KW? Is that your question? You absolutely can. Yeah, and it should give you the same answer. Might be slightly different if you did a little bit of rounding, but it should be pretty much the same answer. So absolutely, you know, if you took the pH and just got your H plus, you then could put it into the KW like we did before and get to your OH minus that way. Yeah. Other questions? All right, let's try some more here maybe. Let's do the pH is 3.14. Why don't we just do it all again here? What is the H plus? What is the OH minus? Let's do what is the POH? And once again, is it acidic, basic, or neutral? From the pH, you really could directly calculate 2 things. You could calculate the POH or you could calculate the H plus concentration from it. We will again start with the H plus concentration since that's really what the question asked for. The H plus concentration would equal the inverse log of the minus or negative pH. Again, when you hit that on your calculator, probably like a 10 and a caret, make sure you hit the negative, not the subtract button, 3.14. I'm going to go with this calculator. I seem to agree with everybody. We'll go with them. We got this minus 3.14. And it looks like we do end up with like a 7.2 times 10 to the 1, 2, 3, 4, negative 4. And it should have a molarity there as a concentration. Again, 2 decimal places, 2 sig figs there in the concentration. Again, one more time, the way you punch it in is your second or shift button top left. Your log button, which should have like a 10 and an X above it, your negative button, and 3.14 hit equals. Again, if you have a non-display calculator, you would start with the 3.14. You would hit the negative button, which would turn it to a negative number. You would hit the second and the log button. Yes. And maybe an equals. You probably don't have to say equals probably on that one. Any questions on that? Obviously, it won't maybe give it to you in scientific notation. So on this calculator, I got 0.00072 and non-scientific, like 4436. Yes. It's two significant figures because the pH value has two decimal places, which means the concentration should have two significant figures. Yes, sir. Which part? That's how you would punch it into your calculator, depending on which type of calculator. So looking at your calculator, you probably will be rolling with that one up on top. Okay. Now, to answer the question that was asked a second ago, you know, if you wanted to at this point, you absolutely could go into the KW, and you could just do the OH minus this way, like we did previously, and it's perfectly good. So if we did it this way, the OH minus would be 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4, and that would get us 1.4 times 10 to the minus 11 in this case. So you again could use that. You also could use the POH once you get it and get to there as well. Question on that one there. What's left here is the POH, which we could get from the pH is equal to the 14 minus the POH. Maybe my mind and hand will work together here. And that is, I wrote that backwards, I know. Okay, so that is, it's almost nap time, you know, it's late. It's time to bed. All I see is chemistry in my head. All right, let's try this. I close my eyes, it doesn't get better. All right, so that is here, the POH is equal to 14 minus our pH. I think that will work a little bit better here. 14 minus 3.14 would yield us a POH of not 17. So that'll be mine. I'll hit. Thank you. I suppose the subtract button would be better than the add. That is a 1086. Thank you. And maybe to answer another question, obviously, if you had that, you could go right into the POH formula as well, and that should get you there. So again, there's multiple sort of ways you could kind of get to the answers, depending on sort of the route you take. They all really should get you to the same answer. Again, you might be slightly off if you did a lot of rounding, but if you don't do a lot of rounding, everybody should kind of get you to the same answers. There's really no wrong way as long as you pick a legitimate way of getting there. So lastly here, acidic, basic, or neutral. It is going to be acidic. That is our pH value, and that definitely is less than 7, so it should be acidic. Question on any of those parts? Yeah. Yeah, so pretty much this was the only number we had, the 3.14. Which means technically speaking, when we did the H+, it should have two significant figures. And really, this is sort of like an exact number to the top guy. So we'd want to maintain those two significant figures for the OH minus, which then also should probably lay us up probably the same number of decimal places on the POH. Yeah. Other questions on that? Yeah. It does. So the KW, like we talked about earlier, will always equal this number. You always have that available to you, even though they don't maybe say it anywhere in the problem. And that's kind of the same idea as every time you take the pH plus the POH, it will always equal 14. So that's sort of this idea. Yeah. Other questions? Okay. Fun with calculators today. We're going to change this and try something a little bit different. Let's do, let's say you have the OH minus concentration is just randomly picking. Let's go with 3.6 times 10 minus 3. Why not? All right, OH minus is 3.6 times 10 to the minus 3. Let us calculate the H plus. Let's calculate the pH. Let's do the POH and one more time for good measure. Is it acidic, basic, or neutral in this case? H minus concentration. So again, we could think about the two things we could directly calculate from that. We could use Kw and go and get our H plus concentration if we wanted to, which then you could use to get your pH if you want to go that route. You also could directly obviously calculate from that the pOH. So I'm going to actually start with the pOH here. And the pOH will equal minus the log of the OH minus. That will get you a minus the log of 3.6 times 10 to the minus 3. So we're going negative button, log button in this case. 3.6 exponent negative 3. So this is different than the ones we've just been doing, the calculation here, like we've been doing earlier. 2.44. Any questions on that there? Yeah. So the concentration has two significant figures. So remember, significant figures to decimal places. So 2 decimal places. So that's why we end up with 2.44. Technically speaking, based on sig figs, it would be wrong. It's not sig figs to sig figs, but it is sig figs to decimal places. Technically, it would be wrong based on if you were looking at how many sig figs, it would be wrong in that sense. Obviously not wrong in terms of the number, but wrong in terms of how you recorded the number. It should have go to 2 decimal places. Other questions? All right, at this point, like I said, we do have a variety of ways you could go. So again, just to mix it up, to do some of the other calculations one more time, I am now going to go back actually and use Kw to get my H plus concentration. So that is going to be H plus. And again, you don't have to do it this way. You could do some other stuff. But just to remind us of some of the other calculations we did, our H plus concentration then would be 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 3. And again, making sure you use your exponent buttons like we talked about. Minus 3 gives us a 2.8 times 10 to the minus 12 molar as our H plus concentration. Now, why not? I'm going to go into the old school pH calculation here, minus the log. I don't know how old school it is. H plus, that is going to be minus the log of 2.8 times 10 to the minus 12. So that one is going to be a negative button, a log button, a 2.8 exponent negative 12. And that will get you like an 1155 here. Now, in this particular case, you will see, based on my choice and some rounding, I actually don't get 14 when I add both of those numbers together, the pOH and the pH, and that's just because of some rounding, but it's pretty close. Obviously, you could still do it the alternative way like we did previously. You could have got your pOH and then took your OH minus as being the inverse log of the minus pOH. And again, that should give you a number wherever we were. Actually, no, we had we were looking for the H plus. I'm sorry. So sorry. Once we could have got the pOH first, is what I guess I'm trying to say, and then you could have got to the pH and basically did that with the pH. You could take the pH to calculate the H plus concentration, and should have got you to that guy by doing the inverse log of the minus pH. Again, you might get a slightly different number, you know, depending on rounding, but it should be in that same ballpark. Any questions on how to calculate any of these things? As you can see, multiple ways you could go. Just choose the correct path and, you know, go that way. Yes, sir. Yeah, so let's see here. Find somewhere I can scribble. Maybe I didn't scribble too much. So here's the deal. If you have either the pH or the pOH, yes, and you want to use those to get to the H plus, R, the OH minus. Those are the calculations where you use the inverse log, yeah, of the minus pH, the inverse log of the minus POH. If you have the opposite starting material, which is like you have the H plus or the OH minus, and you want to get either the pH or the POH, that is the one where you got to start with a negative log calculation. Yeah. So sometimes people get very confused about when I should use the inverse log, when I should use, I know I'm sleeping, it's okay, I'm gonna correct it, hang on. There we go. Or when they should use, obviously, the guy on the left here. So it's really based on sort of what you're starting with and what you want to find. So if you're starting with a concentration and want a pH or POH, that's minus the log of whatever you're starting with. If you have the pH already or the POH already and you want a concentration, then that is when you should use the inverse logs, yeah, which again are those 10s and the carats when you pop them into your calculator. Question on that there? Yeah. Yeah. How to put it in the calculator? Yeah. So I'll just do it right here. Is that okay? It was 1 to the minus 14. So you would type 1. You would hit your exponent button. You would hit your negative button, and you would hit 14. And that will give you basically 1 times 10 to the minus 14. You then would hit the divide button. I'm just going to write it underneath. You then, what was the other number? I'm sorry. It was -3. Okay. So you do 3.6. Again, you would hit your exponent button, your negative button, and you said 6, right? To the minus 6. -3. Thank you. And then you hit that and then hit equals. So again, remember when you hit that exponent button, it represents the times 10 part, so you shouldn't be hitting the multiplication button or anything like that. No log information when you're doing this guy, you know, it should just be straight up that. Yeah. Other questions on how to calculate that? For which one are we talking about? This one? Let me see. So again, you want to type in 1, your exponent button, no multiplication button, just straight exponent button, negative and 14, and then hit divide. 3.6 exponent button, again, no multiplication button, -3, and you should end up with 2.8 to the minus 12. Yeah. Yeah, don't hit the multiplication. So when you hit that exponent button, it represents, one more time, the times 10 part of the number. So you don't have to hit the multiplication or anything like that. All you have left to do after you hit that button is just the exponent part. And if it was negative, you know, put the exponent part. I rounded what now? Yeah. It was, yeah. So it was 2 point, a bunch of 7s and an 8 and stuff. Yeah. It is for a couple of reasons. Basically, in this case, we were really only given 3.6 times 10 to the minus 3, which has 2 significant figures. The 1 times 10 to the minus 14, we probably wouldn't look at because some people use like 1.0, some people use like 1 and stuff like that. So we just look at that number that we were given that has 2 sig figs, and we want to keep it. Yep. Yep. Other questions on any of these calculations? Yes. 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 That's what the exponent button is for. It represents the times 10 part. So when you do that, it does it for you. If you hit it again, it changes it, as you saw, and it kind of does it twice. So when you hit that button, the way the calculator is programmed, it takes care of like the times 10 part for you. So you don't have to hit any multiplication or anything like that. Otherwise, and that's a very common reason why you might be off, is a lot of people still want to hit the multiplication, and that's very common. And again, another very common wrong way to do exponents is to use like the shift log like we were doing. You definitely don't want to use that as well, because your calculator will do some weird, not really weird, it's doing what it's programmed to do, and it's not really the right way to punch it in. So that's why most scientific calculators will have a dedicated exponent button, you know, and you definitely want to always use that. And again, on most calculators, it is the EE button. There's also ones where it says EXP. And remember, as we talked about way back, chapter 2, I think, there are some of the newer calculators that does have that 10 to the n type button. And remember, if you do have one of those calculators, usually will also have like a will on the calculator towards the top. You usually, again, need to kind of put everybody in parentheses still to make sure it does the calculation correctly for you. Like we talked about, I think, you know, way back then. Other questions on that? No? Yeah.
How do you insert it in a calculator when you did, when I ended up using the KW formula?
Yeah.
So I did the 1.0 times 10 to the negative 14 over 3.6. And I end up getting 2.8 times 10 to the negative 12. How do you inverse that so I can get the, how do you do that? The negative log 2.8 times 10 to 12 to get 11.5.
Oh, so if you're asking, whoa. Okay. So you're asking if you had this number and you want to go here.
Yes.
Yeah. Basically, again, it would be, I'm just try to find somewhere I could write here. It would actually be this right here. So no, it wouldn't. So well, I'm sorry. We want to go to the pH. Is that what you're asking? This right here. Yeah. So you would put it in the negative button. If you have a display calculator, you would hit log and you would type in 2.8, your exponent button, your negative button, and 12, I think there, and then hit equals. Obviously, again, if you have a non-display calculator, you would start with the number and then hit the log button and stuff like that. Other questions? All right, fun with calculators. All right, here we go. So let's talk about what happens though, you know, if we do have a strong acid given to us. So up until this point, you know, we've sort of been given sort of generic stuff like the H plus concentration or the OH minus concentration, or again, the H3O plus concentration. Sometimes they may just give you the concentration, actually give you a formula for an acid, like a strong acid. So a good idea is to remind us what are some strong acids. Hydrochloric acid is a strong acid. Nitric acid is a strong acid. Sulfuric acid is a strong acid. Perchloric acid is strong. Hydrobromic acid and hydroiodic acid. So this is sort of a nice little list of some strong acids, which means if you happen to be given a formula of an acid that is not one of those, I would say in our case, you could probably safely assume it's a weak acid rather than a strong acid. And that'll be a little bit helpful for buffers in just a second. But so this list of strong acids, well, basically 100% break apart. So because it's a strong acid, it's a strong electrolyte. When it goes for a swim in the solution, it will stay together. It will 100% break apart into H plus and Cl minus in this particular case. So what's important when we want to calculate the pH and we're told, hey, for example, here you have a 0.1 molar hydrochloric acid solution. What is the pH? First off, we would look at this and know it is a strong acid. So again, it is going to, as we see on the bottom there, 100% break apart into H plus and Cl minus here. So 100%. Out of H plus and Cl minus, which one is important in terms of the pH? The pH equation is the minus the log of the H plus, which means the most important guy there in terms of pH would be the concentration of the H pluses floating around in the solution. So if they told us that this guy was 0.1 molar, we talked about this with solutions, what would be the concentration of the H plus in this case? It is a 1-to-1 relationship, which means the concentration of the H plus would also be 0.1 molar. The concentration of the chloride is also a 1-to-1 relationship, which means the chloride would also be 0.1 molar, although we don't really need that in this particular problem, but just for a reference point, the concentration of the chloride ions that's floating around would also be 0.1 molar. So although they give us the concentration of the strong acid, we can then relate it to what the concentration of the H plus is. And that really is all we would need to go into our pH equation. Because this is a strong acid, it would be 0.1, and that would give us a pH there of like 1, I think. Bless you. Which is definitely acidic with a pH of 1. So like I said, sometimes, you may not be given like a generic H plus or OH minus. They may actually give you a formula for an acid. For our purposes, you could probably safely assume if they do that and ask you what the pH is or the POH, you can safely assume that it's strong. Weak acids is a much, much longer calculation, several pages, and sometimes that's a much longer calculation and stuff like that. So you can probably safely, like I said, assume that it is definitely going to be strong. And really all you need is to figure out what the H plus concentration is in order to calculate the pH. Any questions on that there? And again, this list of sort of strong acids is a good one to not that I would necessarily ask you a question maybe directly like that, but it's a good thing to sort of reference and sort of know. So if we take a look at this one here, this as we look at it is, what is the pH of 0.025 molar per chloric acid? So as I just mentioned, if we kind of look back on our list there, I see perchloric acid on my list here, one of those strong acids. So again, I know that this is going to be a strong acid, which means I automatically know that this guy will 100% break apart into H plus, which is pretty much what an acid is, and really perchlorate here. And again, we're going to have 100% of those ions in solution. Nothing is going to stay together. And that means, just like before, we are interested really in what the H plus concentration is. So if the whole thing is 0.025 molar, in this case, the H plus concentration should be, it is a 1-to-1 relationship, which means the concentration will actually remain the same here. So it will be 0.025. And really that is all we need, for the pH. It would be minus the log of 0.025. And that would get us a pH here of 1.60, which also is acidic, which is good because this is an acid. Now, for example, if it happened to break apart into 2 hydrogens, we would then take the concentration and multiply it by 2, right? And that will get you how you get there. You could also do the same thing if you had a strong base. Remember, a lot of strong bases actually have hydroxide in it. So something like sodium hydroxide would break apart 100% into a sodium ion and a hydroxide ion. And it would be the hydroxide ion that would be important here. It would not allow you to calculate the pH, but you could calculate what from the hydroxide if you knew the concentration. You could calculate the POH, which then you could subtract 14 from and get yourself to the pH. So you could do a similar calculation if you're given a strong base. Again, if this was 0.1 molar, the OH minus would be 0.1 molar, which you could go into the POH equation, get the POH, and then subtract 14 and obviously get the pH from that. Any questions if you're actually given a strong acid or strong base calculation? Yes.
Sure. So you said that the 0.025 is always going to be the same for hydrogen?
It will be, as long as it breaks apart into just one hydrogen on the other side, which in most cases, most of the strong acids, if you look at, are what are referred to as being monoprotic. They pretty much have one hydrogen. So most of them will just break apart into one hydrogen. One exception would be like sulfuric acid. It has two, right? So when that breaks apart, you actually get two hydrogens, which means you need to multiply the concentration by 2. But for the most part, not 100% of the time, but probably pretty darn close. The concentration of the whole thing will be the concentration of the H plus, because it's usually a 1-to-1. Yeah, for this one, the pH would be 1.60. Yeah. Other questions? Yeah. It would be if it was this acid. Again, it's really like we talked about with solutions, the way you relate the whole thing to the ions is kind of like stoichiometry. It's a 1-to-1 relationship, which means basically you take the concentration, multiply by 1. If it breaks apart into like a 1-to-2 relationship, you would multiply by 2, 1-to-3, multiply by 3, and so forth. You could do the long stoichiometry calculation as to really how you get there, but the shortcut is pretty much like that. You kind of do like the mole-to-mole relationship and multiply the concentration by whatever number you got on the right-hand side there. Yep. Good, yeah. Yeah.
Using the top one, sodium.
Yeah.
One, use the pH 14.00 minus, what is the minus 0.10?
No, you would have the concentration here. So if you were doing the top one, you first would have to actually calculate the pOH. And whatever number you get there, which should be 1, actually. Yeah, I'll say there should be 1. At that point, you have the pOH, then you could use that the pH is equal to 14 minus the pOH, which in our above example there would be 14 minus 1, which gives you a pH of 13, which does make sense, right? Because it is a strong base, and that's pretty basic at a pH of 13 at that point. Pretty much, if you look at the periodic table, kind of like where like lithium and there's like sodium and potassium and all those guys. And then you hang it right over like calcium, strontium, barium, basically group 1 and 2 on the periodic table that have OH in the formula. So like calcium hydroxide, barium hydroxide, potassium hydroxide. Those are pretty much a good symbol of what a strong base would be. Yeah. Other questions? Okay, so we're going to then talk about here buffers and a buffer solution and what a buffer is and sort of how it works and all that kind of stuff. First off, a buffered solution is a solution that once you make it, it's able to resist big changes in pH, even if you decide to add more acid or base to it. A very wrong misconception about a buffer is that it is a neutral solution. So it's not necessarily a neutral solution, but it can be. But you could technically make a buffer at any pH you like along the pH scale. You can make an acidic buffer, you can make a basic buffer, you can make a neutral buffer. Pretty much you can pick a number, you can do the right calculation, and you can make a buffer that will stay at that pH. What it means about a buffer is if you made a buffer at a pH of like 4.74, which you might have in lab this week, which is acetic acid and sodium acetate when you put it together. If you added acid to that buffer, the pH would not jump tremendously. It would not go from like a pH of 4.7 all the way down to like a pH of 1. And if you added some base to this buffer, it would not go from like a pH of 4.7 all the way up to like a pH of 10. You won't see very giant swings in pH when you add acid or base. Will it actually move? The answer is yes, it will move in one direction or the other, but not a lot. So if you added acid to this buffer, maybe it goes down to 4.6, 4.7, depending on how much you add, maybe 4.3, but you won't see it make very big jumps. And same thing, if you added base to it, it maybe goes up to 4.8, 4.9, but again, will not jump really big. The reason why it's not able to do that is basically what it is made of. And it is made up basically of one of two combinations. It is either a weak acid and the conjugate base, is sometimes referred to the salt of the conjugate base. That's just a fancy word that says I put a sodium in there or a potassium, not really doing much. It's just balancing out it. The other combination you could have is actually a weak base, and it's salt of its conjugate acid. These are what we were talking about at the beginning of the chapter, which is our Bronsted-Lowry acid-base conjugate pairs. The difference here is just one H plus difference between them. That's exactly what we're talking about here. The salt part, like I said, there's an extra sodium in there, or potassium, not really doing much. They are both in the solution to start with. So for example, if we took a very common buffer, which is acetic acid, which is this guy, and sodium acetate. This is a weak acid. How do I know it's a weak acid? This is where that list I just put up there a second ago is kind of helpful. I don't see that on my list, so I'm pretty much going to assume it's a weak acid. Yeah. Again, that list was all strong acids I put up there a second ago. This is its conjugate base, and this is what is referred to as the salt of its conjugate base. And it's a salt because basically this guy is a sodium ion and an acetate ion. And it is actually the acetic acid and really the acetate part that are the two that are related to each other. If you look at the difference between those two, it is just one H plus difference. Really, the sodium is just kind of hanging out, not doing much. So that is a weak acid and a conjugate base. A weak acid is a weak electrolyte. And if you remember when we talked about weak electrolytes, they mainly stay together in solution. And that's really critical for how a buffer works, because when we put this in the solution, it will actually set up an equilibrium where we will have and be able to keep both of these guys in the solution because of that. And we actually help it out by adding a little bit more sodium acetate, which gives us more acetate. But both of those things are basically going to be in the solution at the start, and they're both in there. Now, this means that we cannot have a buffer that is made up of a strong acid or strong base. So you can never have a buffer that's made up of a strong acid or strong base. That is because if you try to make a buffer with like a strong acid, when you look at what's going to be in the solution, as we talked about, this guy is not going to be there anymore, which means all we have is this guy in there. We don't have an acid part and a base part. And that's really critical for how a buffer works, is it has like really an acid part to it and a base part, and they're both able to stay in the solution at the same time. And that's what allows it to not jump pHs a lot. And we're going to talk about how that does in just a second. Any questions on that? So has to be a weak acid in its conjugate base or a weak base in its conjugate acid. Can never be a buffer made up of a strong acid or strong base, because it just won't be able to function correctly. So how does really a buffer work? So let's take a look really at how a buffer works. Let's take a look at how a non-buffer works. So let's take a look at water, which is a non-buffer. And if we take hydrochloric acid, which is a strong acid, and put it in water, it is going to 100% break apart into H plus and Cl minus. So in the beaker, when I do this, I just made a ton of H plus. That's really important because the pH is minus the log of the H plus. What happens as the concentration of H plus increases? What happens to the pH? It takes a nosedive, right, and goes down. We just generated, when we put it into water, a ton of H plus really quickly. And we would see with water, if you start at a pH of 7, which your water is not going to be, it's probably going to be about 5-ish. And when you start out with it at that original pH, maybe we'll call it 7, you got nice clean water, and you add some acid to it, it's going to jump all the way down to maybe a pH of 1 or 2. And it's going to be a really big jump in pH because you just generated a lot of H plus super quick. Any questions on that? And that's why water is not a buffer, because we do see that really big jump in pH. If we took some sodium hydroxide and dumped it into water, again, sodium hydroxide, a really strong base, it will also break apart 100% into sodium ions and hydroxide ions. And what we just created here is actually a ton of OH minus really quickly. And that's important because as the OH minus concentration increases, what happens to the H plus concentration? Decreases. So we just filled up the beaker with a bunch of OH minuses. That means my pH should head which way? pH should go up. We just filled the beaker with a bunch of OH minuses, going to increase the base part of that solution, and we're going to see a very big jump in pH. Again, if your water started at 7, it may jump to like a 10 or 11 pH, a very big jump, because we basically flooded it with a lot of OH minus, and that decreased very quickly the amount of H plus. Any questions on what happens in a non-buffer situation? Yeah, we should see very big jumps. So what happens though if we put these exact same things into a buffer? So we'll use our example here of acetic acid and sodium acetate. Again, they are both in the solution to begin with. This is really the acid part of the buffer. That is the base part of the buffer. When I go and add my same hydrochloric acid to this buffer, is it going to react with the acetic acid part or the sodium acetate part? HCl is an acid, and these reactions are called acid-base reactions, right? So it's going to react with the base part of the buffer, which is in the solution. The base reaction that's going to occur, which is really a double displacement reaction. And the two positive guys will switch partners, basically. And what we will end up with is acetic acid. And we will end up with a little sodium chloride action happening there. We do see a couple of things happen here when we add the acid to the buffer. First off, we make this, which is a salt. This is what is referred to as a neutral salt. Not going to really screw up the pH. It's all good. It's happy. We also made some acetic acid, right? And the acetic acid was actually part of the buffer to begin with. And that always happens when you have a buffer. If you add something like acid, it will use up some of the base part of the buffer, some of the acid part of the buffer, which is why buffers can resist big changes, because you're kind of making some of it as you're able to kind of keep it there. But more importantly, it is actually what we do not see here on this side of the equation that we did see up here. What do we not see on the bottom equation that we did see on the top equation that would affect the pH? What affected the pH with the HCl and water? It was the amount of H plus that was formed, right? When we add it to the buffer, we get no H plus formed, which means that we did not generate any more H plus, which is good, because that means that the concentration of H plus we started with will remain relatively constant. And if the H plus concentration stays constant, what happens to the pH? It also stays relatively constant as well. And it's because we did not generate a bunch of H plus like we did when we put it in the water. The H plus got tied up with the acetate. It made acetic acid. Is no longer free floating. And it's the free floating H plus that really affects the pH. What happens if we take the sodium hydroxide and add it to the same buffer? It will react with the acid part of the buffer, right? Because sodium hydroxide is a base. We will get the acetic acid that will react. And we will also get a double displacement. Basically, our H and OH and our sodium and our acetate will come together, and we will get a sodium acetate formed plus a little bit of water action happening. Clearly, water is not going to mess up the pH. Just like we saw before, we actually made the other part of the buffer. So we make the other part of the buffer in this case. But it is actually, once again, what we do not see over here. What do we not see over here that we saw in this reaction that was formed that affected the pH? The OH minus, right? With the sodium hydroxide, a bunch of OH minus affects the H plus concentration. We have no free OH minus, which means that the concentration of H plus, because they are related to each other, will also be relatively constant, because this guy will now be relatively constant. And that means that our pH will remain relatively constant. I say relatively because you will see a little bit of movement, but overall the concentration of the H plus will remain the same. So really the way a buffer works, as I end it really quickly, sorry, is that because it has both the acid part and the base part in the buffer, when you add additional acid, it prevents the formation of free H plus in that solution, which would make the pH go really crazy. And because the buffer actually has a base part, when you add, when it has a acid part, add the base to it, it prevents the formation of free OH minus, which keeps the H plus concentration relatively constant and keeps the pH relatively constant. So that's basically how a buffer works. It pretty much prevents the formation of free H plus or OH minus, thus keeping our H plus constant and our pH relatively constant. Question on that?